Well, thank you so much for the opportunity to speak, especially remotely. I am, unfortunately, I'm not able to be there in person this time. But before I start my presentation, I want to mention that just a few weeks ago, we had the most recent conference of the Network Science Society in Vienna, where we also announced the sites for the next few conferences. And as president of the society, it's part of my job to let you all know where those will be. In summer 2024, the conference will be in Canada. You can see the names of the leading organizers here. In summer 2025, it will be in the Netherlands. So those are the summer conferences. But we also have winter conferences. And in winter 2024, it will be in Italy. And here's the interesting thing. In winter 2025, it will be in India. It will be in the beautiful city of Indore. So even though I'm not there now, I hope that in less than 2 years, I'll be able to meet many of you in person. I know that Sarika and Hiroki are putting together a very interesting program, and this conference should be of interest to a very broad audience. All right, so now back to my presentation. I want to talk about work that was completed in collaboration with Shao Duan and Takashi Nishikawa on the localized control of network systems. Even if you're not interested in control or even networks, this should interest you because the ideas are generalizable. I think we have learned a lot of things about networks over the last 25 years, and perhaps one of the most elementary things about empirical networks is that many of them have a very small average node-to-node distance relative to the entire network. And a different implication of this is that as you count the number of neighbors of a node, the number of first neighbors, second neighbors, third neighbors, and so on, the size of this neighborhood grows very quickly as you get farther away from that node. In fact, for networks whose average node-to-node distance grows logarithmically with the network size, this number grows exponentially fast. And it's not very difficult to rationalize why this would be beneficial for networks and why networks might have been designed or evolved to have this property. If you think about communication networks, for example, that means that for information to be sent from one node to another, it has to be routed by a small number of intermediate nodes. In the case of transportation networks, that's what allows us to go from one place to another with just a couple of flights. In the case of brain networks, it's easy to imagine that this could facilitate processing of information. Even for biochemical networks, there is an enzymatic cost to each reaction. So if you can produce biomass with a small number of intermediate reactions, you will be saving ATP. So this is so now ingrained in our minds that it's even difficult to imagine complex networks that do not have these properties. Turns out these properties are also common in the models that we often use. You see that random networks, small world networks, in fact, they are designed to have this property, scale-free networks of various models, including Ordi-Srini, Watson-Strogatz, Barabas-Albert, configuration model. They all have this property, even if the networks are very, very sparse. But they don't have to be that way. If we think about, for example, a regular lattice, the size of this neighborhood grows linearly with the distance from a given reference node. And you can think of other networks that would behave differently. For example, certain types of modular networks, not all of them, but certain types of modular networks like the one I have in front of me now, would also behave differently. Well, I want you to keep this in mind because when you look at the literature in network science, both in network structure and network dynamics, I think the research of network scientists would not nearly as interesting if it wasn't for the curse of dimensionality. There are so many problems for which we have to develop, have to be creative in developing approaches to circumvent the combinatorial explosion that comes with increasing network size. And that is partially related to the properties that I was talking about. Let's take the case of network control. Well, in this case, globally optimal control actions at each node of the network require information about the entire network in order to be determined. And if the network looks like something like this, it's not difficult to convince yourself that, well, the network seems to have a very small diameter with a large number of nodes there. And it's not difficult to come to the conclusion, whether this conclusion is right or wrong, that you really have no way to avoid accounting for all these other nodes because they are strongly influential. So I want to revisit that in a moment. But I won't say this, even if someone has a breakthrough and finds a way to do these calculations in a scalable way, either by developing new algorithms or a new theory or even new hardware to do the calculations, something that no one has thought of before, you still have the problem that for many infrastructure networks, the communication cost would be unaffordable. I want you to think about networks like, for example, the power grid. If you can do optimal control actions in this network, you would be able to minimize cascade size, you'd be able to respond quickly to cyber attacks and so on. But in order to do, to implement those control actions, you have to first sense the state of the entire network, communicate that information very quickly through the network, through a communication network on top of the power grid, in order to have that information accessible everywhere, to then make the control decisions. Even if the control decisions can be done very quickly, you can imagine that the traffic of information here would be unscalable. So the problem is very complicated from that perspective. But there is a possible solution. And here is a way to think about it. It might be the case that you don't need to solve the problem exactly, that an approximate solution is all you need, and that such an approximate solution is scalable. Imagine, for example, that the network looks like this. If the network looks like this, it's very different from the one I had in the previous slide. It's easy to imagine that you might be able to calculate the control actions in each one of these modules by simply ignoring the others. And if you're lucky enough, ignoring the others will not be such a big problem. So you could, for example, calculate for that one and do the same for each one of the others. Well, if that program were to work, then maybe you would have an algorithm that would have polynomial cost, perhaps behave even linearly with the network size, or maybe even saturate. And the good thing about what I just draw there is that the communication cost would be small too, because you don't have to send information all over the network. Well, the trouble with that is that networks do not look like this one I just draw. The empirical networks that we care about look more like the ones that I was pointing to earlier. Which means that if we are to develop an algorithm, even if there's an approximate one, very, very close to optimal, but approximate so that it can be scalable, we have to come up with a completely new method to do that. We cannot just split the network into models in the way I was doing there. And that's what was developed in this paper. and I will be talking about it through the rest of this presentation. The key idea here is the concept of network locality. So we start with the motivation we had before, that globally optimal control action. We use control problem as a motivation. That such actions require information from the entire network, and pose this question of whether nearly global optimal control is possible by only using information from a suitable neighborhood that we hope will be small relative to the size of the entire network. And the answer to this question is yes. I will show you that such neighborhoods can be defined, and they can be defined in such a way that you choose the nodes to put in this neighborhood optimally. They are not always the closest nodes to the node you're interested in. It's more subtle than that, but we have a method that will allow you to optimally identify them in a systematic way. And I'll give you an example now here. This is a small road network, Watts-Strogas model, with a rewriting probability of 0.1. So it's a reasonably random version of the network. I want you to pay attention to node 1. We are giving an example relative to node 1. What's shown with colors here is this information distance that I will introduce to define network locality. I have not yet defined it, but for now, I just want you to know that such a distance can be defined. And the colors are indicating the distance from node 1. You see that there are few red, which means few nodes that are close to 1, and many purple, which are nodes that are far from 1. The purple nodes could be, in our calculations of control later, ignored. You only need to consider the ones that are red. And that means that you have reduced your problem to a much smaller one. Now, the size of the nodes here, by the way, indicate the ordinary node-to-node distance, the geodesic distance. You see there is a correlation between colors and sizes, but they are not the same thing. There is a difference too. So it is this notion of information distance that will lead to the notion of network locality. And network locality will allow us to define, to do control analysis and control design in a scalable way. And here is the good news. Most networks that we studied have small information neighborhoods relative to the network size. Before I show you the results for empirical networks, let's define a few things. So the main equation that I want you to pay attention to here is this one, which we use to define the notion of locality. We say that a network is localized with respect to a characteristic function V and an information metric rho if this inequality holds, where this Cij is really the entries of the coupling matrix. And I'm using this notation because sometimes the nodes have dimension higher than 1. It was just a one-dimensional node. I could just use the number itself. Now, K here is a constant that does not depend on I and J. V is a characteristic function that satisfies some reasonable properties, is monotonically increasing, submultiplicative, V of 0 is 1, and so on. And rho is a metric, which means has those 3 properties that metrics have. Satisfies the triangular inequality, symmetric, and rho of ij is 0 if and only if I is equal to j. So these properties define an algebra that's closed with respect to matrix arithmetics. But if in addition to that, you also impose this condition, then that the set of matrices that satisfy those properties plus this condition will also be closed with respect to matrix inversion. And with that additional ingredient, we can guarantee that the solutions of linear equations, the solution of the Riccati equation, the solution of the Lyapunov equations, all preserve locality in the sense that they inherit the locality from the network. And since these are the equations that you need to do control, well, that means that then you can really fully benefit from this property as you design your control actions. The choice of V is not unique. We chose this function where alpha was taken to be 1, beta is smaller than 1, and Q larger than 1. And rho is a geodesic distance on an auxiliary weighted graph, which is in particular undirected. So once you have all of this, then you can start having some fun by applying it to networks of choice and see what you get. So I will show you a few examples here. And there are different ways in which you can use those quantities. So here's one. You can define a gamma neighborhood. Gamma is a number between 0 and 1. And if you take a node, I, that's at the center of my ellipse here, and you measure the strength of the interactions of node to each one of the other nodes in the network. The strength of interaction is the inverse of the distance I just spoke about. There will be one node to which it is most strongly connected, between quotes. And I want to use that node as a reference so that I will define a neighborhood of all nodes that have an interaction strength with my node I that is larger than gamma times that largest interaction. And those that are weaker, I say they are outside my neighborhood. So once you do that, you can then introduce an average over all nodes I in the network that I would denote by S. So that's the number of nodes in this neighborhood, average number of nodes. And you can further normalize that by N if you want to have a number that's between 0 and 1. Strictly speaking, for a finite size network, it will be between 1 over N and 1. That's L. L bar, S bar, and L bar. Okay, now let's create some space here and plot something. We have we selected and curated carefully a diverse set of 50 networks from a public database, Connect. We didn't cherry pick these networks. We chose them to maximize diversity. So we had networks from various domains that are marked here on the bottom. And I will plot here this average neighborhood size as a function of network size, because these networks were chosen, some to be smaller and others to be larger. We have to choose a gamma for this, and we are using a gamma here that is 0.05, which means we are choosing neighborhoods so that we exclude the interactions that are weaker than 5% of the strongest ones, and which is equivalent to saying that we are choosing the closest distances and dropping the ones that are the nodes that are farther away information distance wise. You can already see from my scale here that there is a significant difference between horizontal and vertical. So let's see how this looks like when I throw in the numbers out here. So you can see that we have here color-coded points indicating the networks that come from different domains. And there are dotted lines also indicating L bar. So you see that S is equal to L bar times N. So in a linear scale, these would be straight lines, but because you had to plot linear log scale, they are curved. Almost all networks have an L bar is smaller than 10 to minus 2, meaning the size of the neighborhoods is smaller than 1% of the size of the network. And doesn't seem to depend on network size much. That's very clear for the three models that are plotted. In addition to all the empirical networks, there are three models here. ER is the Ordich-Rene model, BA is the Barabas-Albert model, and WS is the Watts-Strogas model. You can see that's almost horizontal for those. And that really means that the network size can increase while the neighborhood size of interest remain essentially the same. So it saturates actually, which is perhaps better than we could expect. Now here we are in a sense taking a decay rate and quantifying the neighborhood size. We could also do the opposite. We could take the neighborhood size, which I will now denote by L, and calculate the decay rate. Here is for a selection of those networks. The model networks have size 1,000. And you see that this goes down very quickly at logarithmic scale here, meaning that even for relatively small L, 5, 10, 20, you already have most of the information that you need in all the networks that I'm showing here. Okay, that's good news because it means that these networks, even networks that are very unstructured, like arbitrary networks, can benefit from this concept I introduced earlier. And you can then use that now to do localized control of networks. Can do other things, and we have other projects where we are exploring other properties and other processes. But here I want to talk about control, which was also covered in that same publication. Start out with an example of a power grid network. A lot of things can happen in a power grid, but the example I want to consider here is the example of controlling instabilities in the power grid. I will use the example of the largest interconnection of the North American power grid, the Eastern Power Grid Network, which is shown here. And in the control literature, the problem that I'm referring to would be known as an equilibrium stabilization problem. And we will choose to implement it by controlling the input power, which is the mechanical power in a traditional power generator, if you wish, at each generator node in the network. So just so you know that the equations that we are using are nonlinear, we are modeling this using the swing equation. PE here is a nonlinear function of the dynamical variables. And this is a structure reduced model. We apply a Cron reduction to transform non-generating nodes into equivalent impedance. So at the end of the day, you have just generators as nodes, and they are connected to each other through these orange lines that represent the information neighborhood connections. Now, for this model, we have nearly 4,000 generators. So that's the number of nodes in this network. And what I will show in the next slide was implemented using neighborhoods of size 10, the node plus 9. At each node, the control decisions are made based on the information at the node and 9 others. Which again, I emphasize, those 9 others, they are chosen using that the methods that we developed, which means sometimes a node is not a neighbor of a first neighbor of the node of interest, or even a second neighbor. It might be farther away, but happens to be closer to that node in terms of information distance. Okay, so in that network, about 30% of the energy is renewable. And the perturbation that we consider here was one in which the renewable energy generation was shut down at time t equal to 1. Well, if you have global control of the network, you would that would bring the system back after a while. And then there are at time 4, half of the lost power is brought back, and at time 7, the other half. So there are three perturbations, if you wish: the initial cut off power, and then the restoration at 2 steps. And so the top two panels here show what happens when you have global control for the phases and frequencies of the system. This is the United States, the frequency of interest 60 Hertz. In the absence of control, is what you have is what is shown in the bottom, and we are here integrating beyond what would be physically reasonable. The system would shut itself down before then, just to show you how bad things go. Now, what is interesting is that even if you are limiting yourself to just 10 nodes out of nearly 4,000, the local control performs almost as well as global control. That's what's shown is on the right here. And there is a summary in the bottom panel confirming what I just said. So it does seem to work very well. And that's good news, because in practice, you would not be able to do global control. We are doing that after the facts here, but in real time, the time that took us to do this calculation for global control is much longer than the reaction time to implement it. So if you do global control, you might have a very precise, exact control action that's truly optimal, but it will be available to you too late when it is already obsolete. It will be telling you what you should have done in the past. So with local control, you don't have that problem. Another example here is for the spread of an infectious disease, assuming that the main drive is air transportation. This is a network with 2,200 cities connected by air transportation. And I'm showing here, relative to New York, the information distance of the other cities in the world. You see by the color is coding information distance. Again, the size is the ordinary distance on the graph. And you can see that it's a relatively small information neighborhood, again, as expected. It's a localized network. Perhaps less surprising than in the case of, say, an arbitrary graph, because this network is embedded in a two-dimensional space. The models that we use to consider this is, and you should regard this just as a proof of principle, is again nonlinear, with S indicating the number of susceptibles and L infected. And in the context of control, this would be a trajectory tracking problem. And the actions to intervene are vaccination and treatment. So if you do not, I noticed that we have 5 minutes. If we do not have, yes? Right, thank you.
Adilson, just
Okay, thank you. I have just a few more slides. If you don't do anything for the simulations that we consider here, it will take about 2 months to pick for the number of cases to pick. But the interesting thing is that, again, local control with just 20 cities out of 2,200 performs as nearly as well as global. And again, proof of principle. Okay. Another example for brain dynamics, just so we exercise different types of dynamical models. 2 different layouts here for the same data, one in the original brain configuration, the other is in the plane, showing the information neighborhood relative to the node that's marked by the arrow. In this case, the model is given by this definite set of equations here. And here, we are considering the case in which you have a pathological dynamical state, which oftentimes means bigger amplitudes of oscillation. So the problem then is a common following task. You're trying to bring it back to the healthy behavior, which is indicated by green here. And with localized control using just 10 neighbors out of over 600, you have 9 neighbors, the node plus 9. You have good performance here too. So these are examples, and we have considered many other systems that are even easier to exercise under a wider range of conditions, like coupled Kuramoto oscillators. It seems quite general that you can reduce significantly the computational burden in the context of control by taking advantage of the property that I was talking about. So what property is that? Is that many networks are localized in the sense of having a very small, very small information neighborhoods relative to the number of nodes in the network. And in the context of control, that means that near optimal control actions are possible by systematically using data from these small information neighborhoods. In many cases, the state estimation and control of large networks will be possible at the cost of small ones, because as we saw in one of my first plots, the information neighborhood size seems to saturate with network size. Of course, that depends on the model, and I can design counterexamples if I want. But if you believe that some of the models we often use represent first approximation empirical networks, that is a reasonable thing to expect. We have codes for all of these available with the publication, so they are ready-to-use codes. But I want to emphasize that these concepts, they are relevant beyond control. And there are many other things that one can consider by exploring these ideas that I was talking about here today. I'll be interested in discussing with other people that might be interested in different applications. Thank you very much.
Thank you very much, Adilson. Time for a few questions. Yeah.
Would a localized control system still work if there is a hyper exponential growth, like the delta wave that happened in India? It was a hyper exponential growth. Could we control such growths also using a localized control action?
So when you say hyper exponential growth, you mean of what with respect to what?
It's the pandemic is spreading in a hyper exponential fashion. So within a finite time itself, it can like really blow up compared to an exponential growth. Like the mutation brings about the hyper exponential nature.
What process are you thinking about? Power grid, blackouts, things like that?
No, disease spreading. The COVID.
Like spread of diseases?
Yeah.
Yeah.
COVID.
Yeah. So, yeah, I think one has to always be very careful about what models can tell you versus what reality will tell you, right? I think within models, I think there is a broad class of epidemic models to which what I was describing would apply. I cannot make a decisive comment about that particular case you are bringing up, but even if that's the case at the model level, I would be careful to draw conclusions about the real system for multiple reasons, including that epidemics do not spread through only through networks. There is more to it. There is first, the networks that govern epidemics, they are not just pairwise static networks as the ones I was considering here. They can be time dependent, they can be multi-layered, they can be involve higher order interactions, all sorts of things. And I think it would be relevant to consider these other things too, if you want to draw conclusions about real epidemics in the real world. And you're right, maybe the super exponential aspect that you are describing would be something that would bring new conclusions here. It would be interesting to look into that.
All right, thank you.
Any other questions? Rahul.
Hi, thank you for the very nice talk. I was just curious if can we infer like the locality of a network just out of like the data that we have, because in all the examples, if I'm not wrong, we already know the structure of the network, right? But in much like situations, we don't know that. But I was wondering if we can take some insight from the data using this localized measure?
Yes, yes. No, that's a very good question. Excellent question, right? We want to use this, for example, in a social network. We would like to be able to do it in a decentralized way, right? And yeah, so that's work in progress. And I would say that it seems
Can be said.
possible. Now, how general it would be is not yet clear to me, okay? Because you have to make some assumptions about what you know in the absence of knowing the network structure, okay? And I think I would save the rest of that for a future presentation when I have more to say. But this is a very good question. It's really a very important question indeed.
Okay, thank you.
We look forward to that, those results.
And just to substantiate why this question is important is also because the control actions themselves in such networks are oftentimes limited to being decentralized. Just think about, for example, immunization in a population using the Friend's paradox. One of the reasons why that's appearing is precisely because it only uses local information.
Okay. Good. Well, thank you very much, Adilson, and thank you for participating, even though it was long distance and we wish we could have had you here.
No, thank you. It had been a long time since I saw the sun rising. So I had today the opportunity to wake up very early, and it has been fun. I hope I'll be able to participate in the discussion that will follow.
And
Thanks.
we'll give you many opportunities to see the sunrise. Okay, thank you. Bye-bye.
Thank you.